Hello, everyone. Thank you for joining us. My name is Asmin Daher. I'm an architect at Beirut Heritage Initiative. If you have any questions, please write them in the chat box and we'll answer them at the end of the presentation. Today's presentation, Efficient Building Renovation, will be presented by Aram Yeretzian, an architect and professor at AUB that focuses on climate-responsive buildings and sustainability issues. Aram?
Yeah, thank you, Yasmin. Can you hear me?
Yes.
Okay, great. So good afternoon, everyone. I'm really happy to be here to speak about a subject that is really dear to me, to which I actually put in a lot of time in terms of research within the academic context. Window. Can you see the slide?
Yes, it's very clear.
Great. So we're talking about efficient renovation. The talk will kind of cover several aspects. First, an introduction, then I'll be addressing a bit the context, and then I'll move on to the actual issue of renovation. And I will talk a bit about this term, and then we will look at a couple of examples of actual buildings and what we can learn from what is happening to the older buildings. I like to start with this quote from Anne Lacaton. As you know, they got the Pritzker Prize this year, and in their acceptance speech, she mentions that the existing building is tomorrow's new building material. It's about considering the existing as a resource and as a value, and not always seeing it as an unsatisfactory and constraining element. So I think this is very, very telling. Existing buildings are, in fact, the way I see them, they are an integral component of what makes a sustainable city. The majority of buildings in a city, and in this case I'm talking about Beirut, are of course an existing building stock. So 75 to 80% of the buildings in Beirut were built before the early to mid 1970s. And this is, again, a very important parameter to start from. Since they exist and they are inhabitant and they are an integral component of the urban fabric and morphology, they require to be refurbished. This is the natural way that things happen in the city. In our case, given the situations and the wars and the explosions, etc., this becomes more of a critical aspect, right? The issue of renovating old buildings. As you can see in this study, this is taken from Coloring Beirut. It actually identifies the ages of buildings, and a lot of them are, in fact, within the eras of the modern period, right? What Dr. Arbid, what George referred to as the modern period. So we're talking about the 40s till the, well, it says till the 90s, but in fact, it's prior to the Civil War. This is also, okay, this is also underlined in a study done within the Hamra neighborhood. This is the UN habitat, whereby, again, it shows that most of the buildings in the Hamra area pertain to these eras. And so this is just to say that many of these buildings exist, are old, but require work to be up to standard. My premise is that when you look at the city of Beirut, right, we're looking here at Beirut in the 20s, let's say, as a map and as a picture, the environment was very different. This was an environment whereby buildings had limited heights. The ratio between the built and the open spaces had a particular value. Building materials were also particular, as was addressed in prior talks and lectures. As well as the density, right? The density of the buildings and their disposition within the city. And this created to a certain extent, an environment that was very welcoming and that was to a certain extent very quote unquote sustainable, what we refer to today as sustainable. Of course, sustainable goes beyond the buildings, it goes into the food, the agriculture, the transport, etc. But all of that actually did constitute a very strong base for what we refer to today as sustainability. If I move forward a bit into the next decade, so this is again Beirut in the 30s. You will see how, of course, it is growing. The buildings are being dispersed, so the nature of the city is changing. The nature of the buildings are changing at this point with the introduction of cement, etc. Buildings are a bit higher. They are changing kind of character, and to a certain extent changing, built with different building materials. But again, the context remains, and the environment in general remains very welcoming in terms of building design when we refer to particular aspects of passive strategies and the integration of passive strategies. So the fact that buildings were low, the fact that buildings were dispersed, and they were built with particular materials, meant that these buildings could benefit from passive strategies such as natural wind flow, for example, to allow natural ventilation. The sizes of the openings allowed for proper airflow within the spaces. They kind of controlled the incident solar radiation, and they allowed for adequate amounts of daylight inside the spaces, right? So we did not have yet the big glass facades or to a certain extent, of course, the glass buildings that we see today. So I'm saying that the environment was different. The environment allowed the buildings to adapt in a certain way to the passive design strategies, and that created a sense of comfort for the people living in the buildings. So there was a symbiosis, right? There was this synergy, this harmony between the buildings themselves, how they responded to each other, how they responded to the greater environment, and how people actually behaved within these buildings. Today, the condition is completely different, right? We see the city today, urbanism has taken its toll. Things kind of got out of hand at a certain point. Beirut today, the density of buildings is very, very different. The proximity of buildings, the ratio of built-up space to outdoor green space, to parks, to piazzas, is very different. Of course, it has evolved in a negative manner. The heights of buildings has changed, and in fact, the quality of the construction in most cases has also differed significantly. And this is creating a new environment, right? This today's environment is very, very different than what we had in the 20s, in the 30s, even 40s and 50s, right? So to a certain extent, we are faced today with this condition whereby we have very old buildings, except that they live in a new environment. So have they adapted to this environment, right? To what extent can they adapt to this environment? Today's buildings, the people living in buildings use up a lot of energy. Okay, this is a very recent study done by the Italian ministry as well as the Ministry of Energy in Lebanon and the LCEC, and it shows this was a survey that was done, and it kind of indicates, of course, based on the different climate zones in Lebanon, but if we look at the coastal 1A, which is the majority of the urban condition, which is in Lebanon, is found in the coastal 1A, you will see that a lot of energy is used for cooling, right? So this is a direct condition or a result of the quality of buildings, the urban fabric, and the environment in general. So we are kind of seeing clearly here that we have an issue that requires to be addressed. Moreover, and which becomes really a serious problem, it's the fact that this will not become better with time, right? In fact, as seen here in another study by UNDP, very recent. It's a couple of months old. These are projections for the temperature. So these are the days when you will have temperatures above 35 degrees, right? And so currently they are about, let's say, 6 days. In mid-century, they will become 36 days, which is a tremendous increase in days over 35, which of course means that many more days will be above 30, and this is very, very uncomfortable. And of course, towards the end of the century, the projection is that we will have 77 days, right? A good quarter of the year that is above 35 degrees. And these are alarming numbers, right? These are really problematic. The issue being that a building that was built in 1950, given the environment that I described, provided comfort to a certain extent to the inhabitants because of the environment, because of the design, etc., and the construction method, of course, whereby today it is no more comfortable to live in these buildings. And I think we can see that. I will show you some studies that I have done, but we can also see that from colleagues and relatives and people living in these buildings and the problems they have. And this is, of course, really magnified today with the lack of electricity and the lack of support, generator electricity, etc., whereby people are living in these spaces and they actually experience very, very difficult thermal conditions. There's a lot of thermal discomfort. So if this is today, what will happen by mid-century, right, which is in 20, 25 years, let's say, and then what will happen later on? Of course, the situation will become much more dire and much more difficult to live with. So the issue of renovation, I need to address this subject because, or this term, I need to address this term because of, I believe that we need to be accurate with the terminology. So renovations are projects whereby the structure, in fact, building, is restored or repaired to its initial kind of condition. This is fine to a certain extent, but it really, from my perspective, does not comply with what needs to be done so that we produce and set up, if you like, spaces that are compliant with today's requirements. Requirements being the urban context, as I mentioned, requirements being the expectations of people that have changed over the decades, and requirements being these issues related to thermal comfort, of course, and the associated energy use. So the proper term is retrofitting, right? So I would like to continue from here on using the term retrofitting because this involves, other than renovating the actual building, it involves including and improving, let's say, the performance by, of course, integrating new technology, right? New building systems, maybe modifying somehow the building envelope, as we will see in a bit, either the wall or the window. So the term retrofitting seems to be the proper term because it actually wants to bring back the building to its initial state, but it also wants to improve the performance so that it complies with the requirements, not only of today, it should be of the future, right? So today we need to take into account climate change and actually work on these existing buildings so that they will provide comfort in the future. I also like to refer to the term conservation, which is much more strategic and global. This is, in fact, it addresses all the processes so that a place or a space retains its cultural significance, right? And this is, of course, of primary importance to us as architects and planners and experts in this field, or specialists in this field, whereby it's not really about the formal aspect of bringing a space back to what it looked before, or even to implement some measures to actually make it perform better, which is, of course, important. But the main essence here, because in the broader sense of things, we want to address the sustainable dimension of the city. In fact, we need to look at the significance of the aesthetic, the historic, scientific, and spiritual value, right? And of course, it's so interesting because this will relate to, in fact, the past. We need to look at the past, learn from the past, understand the past, continue within the future. Our role is today, and then the age of buildings will outdate us. So we need to pave the way for the future generations so that the buildings, in fact, perform better in the future. So perform, in this case, I'm not talking about the technical performance or the energy performance. I'm actually addressing aesthetic, historic, scientific value, which is in fact what makes the culture, right? What is the key to the cultural aspect of a sustainable city. Okay, to do this, in fact, retrofitting will require the intervention and the collaboration of a multidisciplinary team. The architect, the material specialist, as we will see in a bit, is very important. Understanding the behavior and the physics of materials, also referred to as a building physicist. The MEP consultants and experts, structures, of course, heritage expert, and then other, depending on the typology of the building or the typology of the group of buildings, in terms of urban context or social context or economic context, right? So there's always a broader picture which always refers to or relates to sustainability. But in terms of the building itself or the structure itself, this would be the minimum team required to address such a problem. We know that many aspects affect the sensation of comfort indoors, right? So if we the whole issue of energy efficiency, of course, is to use less energy to reduce the demand so that we can enhance and improve thermal comfort and well-being by using passive measures, right? So we want to feel comfortable indoor by using less energy. We're not saying that we don't want to use energy at all. Of course, we may need to, particularly on the peak days when it is extremely hot or cold, very hot or cold. But in general, we can really extend our sensation of comfort indoors by relying on passive strategies, which in fact relate to the building fabric in existing buildings. One very important aspect is, in fact, the surface temperatures. So we feel comfortable. This is due to a term which is the mean radiant temperature. A person in a space, the sensation of comfort is dependent on the mean radiant temperature. And that is, in fact, resulting from the temperatures of the internal surfaces of the walls, the ceiling, and the floor. So in general, if you're sitting in a cubic space, let's say there are 6 surfaces, 6 planes, the average of the temperatures of the internal surfaces of these planes constitute what is called the mean radiant temperature, and this is really one of the key elements that affects our sensation of comfort. If the internal surface of a wall is very cold in winter, this will affect our sensation of comfort because we will lose heat to that surface and we will not feel comfortable. Similarly, in a hot context, if a wall is very hot, it will be radiating heat to the inside, and that will again result in thermal discomfort. I'm looking here at 2 buildings. This is a building which is on Makhul Street. This is an old house built in the 1920s. The typology is very much, again, like what was described in prior lectures, and it has the central dar typology with the protruding balcony and the open central space, which allows for natural ventilation. It allows for adequate daylight, and it is built with sandstone walls that are about 23 to 24 centimeters thick that are plastered with lime plaster. This was very, of course, common during that era. So this is kind of one type of house that I want to talk about, or I will say one type of wall, a wall type. And the second, in fact, are the buildings that were built in the 40s and 50s, right? Particularly late 40s, early 50s, etc. As an example, I'm proposing here a very interesting project by architect Farid Trad, and the building is, in fact, if you look at the plan on the left, I'd like to say a few words about the passive design aspect. So again, if we go back into the 1940s and 50s, air conditioning was not really very common in the city of Beirut. So significant effort was done in terms of building design and construction to again benefit from passive design measures. So in this case, if we look at the plan, you will see on the bottom left hand the north sign pointing upwards on the plan. That's why I put the plan upside down in terms of the writing. So the north is upwards, and then you will see that, for example, the position of the kitchen, which is towards the northeast, is in fact positioned so that the prevailing winds that come from the southwest will just ventilate the kitchen towards the external environment. You will notice that all the bedrooms receive east and south sun, which is always very beneficial and helpful. And you will see that the balconies are in fact covered, and there's a parapet, etc. So there's a certain amount of effort done in terms of shading, right? Another interesting dimension in terms of passive approach is wind flow, right? So all these rooms, in fact, you notice have two openings. This will allow more wind movement within the rooms of course, to ventilate the rooms. You will see that the openings are also oriented towards the southwest. So you see with even of course the dar, which is open as a facade, so the balcony is shading the actual glazing component as you see in the picture, and then the wind can flow into the dar, into the ghurfat al-ta'am, the dining room, and then go out the other balcony situated towards the north. It's very interesting to note that you have a balcony to the north and the balcony to the west and the balcony to the south, and this also allows the inhabitants to change outdoor seating conditions depending on time of day, which is a very interesting idea that we have in the vernacular architecture much earlier on, around 1850. I will end by saying that the stair is also contributing to the strategy of wind flow, because the stair is in fact aligned around an opening. This opening, due to buoyancy, will allow natural vertical wind flow, and it will ventilate the building as well as the entrance spaces for all of these apartments. A last word about daylight. So the sizes of the openings and the location of the openings inside the spaces of the apartment, as well as, of course, the stair, allow for quality daylight, right? These openings are not large, and so therefore they will not result in glare, in problems of glare inside the spaces. The only large opening is the dar, and in fact it is shaded by the balcony. So there is a lot of sensitivity and sensibility. This is why, in fact, I'm presenting this as a really good example of a climate responsive building of the modern era. A note about the shading devices. If you look at the picture, these were very interesting shading devices. They would roll up and down, and they would also pivot. So it's a top-hung system that can pivot outward, as you see in the windows on the left. And this actually allowed and provided opportunities for multiple options. Either they are closed because, to block completely the sun and the light, let's say, or they could be pivoting, so open to block the sun but allow wind, or they can be open completely depending on the orientation of the sun, the time of day, and time of year. So again, a very simple tool and device that provided a multiple possibilities and options, and I would say opportunities, to make the internal spaces more comfortable. Now, having said that, I come a bit to, so this is all work that I've been doing at, this is part of a URB study at AUB. This is pending publication, so I really cannot circulate this. I'm just, sharing it here in a brief manner, but I think it's very important to see what's happening. So this is the month of August. The chart shows the month of August, and the black line is the variation of the outdoor ambient temperature. right? So these are the fluctuations. It goes up and down in terms of temperature. You will see it varies between 26, 27 to about 31, let's say. This is again in August, and this is the outdoor temperature, ambient temperature in Beirut. This is all measured data. And then for a wall of a building built in the 1950s, such as the one we just saw, the red line represents the internal surface temperature of the wall. So briefly, just to mention that I actually I take measurements, I place thermocouples on the wall, on the inner surface and the outer surface of the wall, and I leave a device that will log in temperature every hour for a full year. So I can see what happens throughout the full year at every hour, as I will be sharing in a bit. Of course, this is all compared with the outdoor weather station that I have installed, which gives me the ambient conditions in Beirut outdoors. So you will see that the red line fluctuates a lot, right? So this is a thin wall. The common method of construction in the 40s, 50s was to have a thin wall. In many cases, it was a cast concrete wall. During that time, they used to use pebbles instead of what we call today as aggregate. So these were round pebbles, and in fact, at that point, the reinforcement bars were not even threaded; they were smooth bars. But anyway, that's a detail. The idea here is that this is a wall that is 14 centimeters thick, and you will see that the internal surface temperature fluctuates a lot, which is in fact the red line. What I'm showing here with the green line is exactly the same thing, the internal surface temperature, but for the wall that was built in the 1920s, the first picture I showed you. And so you will see that there's a very big difference, right? The wall in the 20s that has a total thickness of about 30 centimeters, including the lime plaster outside and inside, really fluctuate. The internal surface fluctuates much less than the thinner cast concrete wall built in the early 50s. And this is, in fact, very, very important, right? This is when we want to renovate, when we want to retrofit buildings. It's really important to understand these parameters, these criteria, so that we can, in fact, address the building envelope in a particular manner. If I go a bit further, these charts here, these graphs will show us, in fact, the indoor surface temperature throughout the day. So again, it's really interesting, I mean, for me to look at these and then to understand that throughout the 24 hours, how is the internal surface temperature varying? So this is kind of a zoom in to the previous chart. On the left, you have the building of the 1950s or the wall of the 1950s. On the right, it's the wall of the 1920s. Again, you will see here that we mentioned that the 1920s wall internal surface temperature is much more stable. It fluctuates less. In the 50s wall, it's fluctuating a lot more, except that here we can see per hour throughout the day what's happening. Of course, this is important because we associate this with the usage of the internal space, right? So if it's a bedroom, it's one thing. If it's a living room, it's another, a kitchen or a service space, so on and so forth. So it's important to identify what is happening during the hours of the day. If I move forward, we look here at the difference between the indoor and the outdoor temperature. Again, the interest here is that in the wall of the 50s, because it doesn't have a lot of thermal capacity, it is a thin wall and it is a dense wall, you will see that the difference between indoor and outdoor is pretty much flat, right? Of course, I'm looking on the chart on the left, the graph on the left. This means that when the difference is little, it means that whenever it's fluctuating on the outside, on the outer surface of the wall, it's also fluctuating on the inside. So they're going hand in hand together. Whereby in the wall of the 20s, you will see that there's a much bigger difference. So when it is fluctuating on the outside, it's taking time before it actually fluctuates on the inside. And this is, again, an important consideration when we want to think about the overall holistic approach to retrofitting a project. I will also show this chart, which is in fact how the indoor surface temperature varies throughout the day. So this is a day in April. Now here what is interesting is that we've been looking at August, which is the hot day. And in August, we really don't want the internal surface temperature to fluctuate a lot, because when it is hot outside, it will become hot inside, and that will affect my thermal comfort in a negative manner. Whereby in the 1920s space, I will be much more comfortable because the wall is absorbing the heat, and internally there is much less fluctuation and variation. In April, so here this is a month in Beirut where the temperature is very mild. It's in fact very comfortable, let's say. In this case, you will see that the indoor surface temperature is on the left is the I forgot to mention, it's the house it's the wall of the 50s, and on the right, again consistent with before, it's the wall of the 1920s. So in this case, when the temperature outside is actually favorable and comfortable, I am interested in having the wall perform this way, right? So when outside it is 19 or 20, etc., I would like it to be 19 or 20 inside. And the pepper dot diagram on the right, in fact, is showing the outdoor surface relative to the indoor surface. The fact that all these points are very close to that diagonal line means that the surface temperatures on both sides are equal. So the conclusion here is that the performance of a wall depends on the season. Right, there is no black and white situation. There is no, we cannot conclude that the 1920s wall is better throughout the year or the 1950s wall is better throughout the year. It turns out that all of this data and this analysis shows that when it is really hot or cold in Beirut, of course, based on Beirut's kind of sensation of hot and cold, the 1920s wall works well. However, during what we call the mid-season, right, the spring and autumn season, in fact, the 1940s wall works better because I'm interested in having indoor temperatures that are similar to the outdoor condition. And so this kind of creates a very interesting notion. How do we go about designing walls, right? What do we do? I mean, how do we intervene? How do we retrofit? Is this related to the typology of the space inside? Is it related to the time of use of the space, so on and so forth? So that we go deeper into the considerations of the usage of the space, so that we can actually articulate and define in a better manner what is the methodology required for retrofitting. This is the last chart. Again, I'm in August, so two very important parameters, indicators to look at when we do this kind of work. The first is, in fact, what we refer to as the thermal time lag. This is the difference. This is, in fact, the time difference between the maximum outside and the maximum inside temperature. So when does the outdoor surface temperature reach a maximum with respect to when does the indoor surface temperature reach the maximum? So the time it takes is referred to as the thermal time lag. The other factor that you see here on the right is the decrement factor. And in fact, the decrement factor is a ratio, right? It's a ratio between the difference of maximum minimum temperatures inside over maximum minus minimum temperatures outside. I don't think we need to go into the physics of this, but the bottom line in these kind of criteria is that when a wall has a higher time lag, thermal time lag, and a lower decrement factor, it actually works better. And this is, in fact, what we see in these charts. We see in the graph on the left, the wall of the 1950s, you will see that there's practically no difference between the outside surface and the indoor surface, the red and the green, and the blue lines, whereby on the right you can see that there's a slight difference of 2 or 3 hours, which I'm showing with the two vertical lines. So there is a thermal time lag in the 1920s wall, and there's no thermal time lag in the 1950s wall. This is just confirming what we were saying prior. This is a study done on the 3 hottest days during August. And in fact, the decrement factor, similarly, the decrement factor for the 1950s wall is around 1.1, let's say, whereby the decrement factor of the 1920s wall is well below at about 0.35. And so therefore it's really clear that depending on in this season in August, the actually the 1920s wall is working really well. It's very performant. Another study that I'm working on actually highlights some parameters. So this is work that was done. We took a space that was designed in the 1950s with the characteristics of a 1950s building in terms of wall fabric, window wall ratios, natural ventilation rates, so on and so forth. And we kind of, so we modeled this on Energy Plus and we linked it to MATLAB so that we can implement variations. So after validating the model, we actually implemented some variations. So just as an example, I will show you that, I will share that, when you improve glazing, of course, in the 50s, glazing was simple, single glazing. When you replace that with double glazing and with profiles that have a particular improved performance, you can reduce energy consumption by about 10%. This is throughout the year. Of course, mainly it is cooling because this is in Beirut. If you add internal thermal insulation, as shown in this picture, so there are these boards that come with thermal insulation and plasterboard on the inside, quite easy to install. So installing these on the inside of the wall will improve and reduce energy consumption by about 18%. And if the spaces allow, and if people are kind of agreeable to this, we can add a second wall towards the inside, right, with a 5 centimeter gap. So this was also simulated, and it actually, when doing the wall, when actually building the wall and changing the glazing, we can improve and reduce energy consumption by about 25%. So this is really very significant, and I kind of reiterate that today with everything that's happening, this becomes really very, very important to address within existing buildings. There are many other options, right? So depending on the building typology, in some cases, and of course depending on the economic aspect, in some cases the second wall can be applied to the outside. This is done a lot in Europe, particularly in England, because the rooms are very, very small and they cannot allow losing, for example, 15 centimeters or 12 centimeters along the periphery of the wall. So in many cases, if there's no architectural value to the building from the outside, there's another layer, a double wall that is put. In many cases, if it's a brick building and the brick is exposed, there's another brick wall that is built at a few centimeters from the existing one. So in a certain way, the actual visual aspect does not change, but of course the performance is much better. Here, maybe I can mention that in England, in London, let's say, there are many old buildings. Irrespective of the age of the building, all of these old buildings have to adhere to the contemporary requirements in terms of energy consumption. Okay, so this is a very important aspect that we need to deal with in the city. A word about active systems, right? So these are kind of very common today. They're becoming more accessible commercially. Of course, this is based on supply and demand, etc. And we see, particularly over the past few weeks, that many people are interested in addressing or integrating active systems in the form of PVs or solar thermal or other within their buildings. It's very important to actually maintain these systems. I want to say in terms of retrofitting. So first of all, proper maintenance will extend the lifespan of the MEP system, basically of the mechanical system, be it heating or cooling or ventilation, right? And of course, extending the lifespan is much better than constantly changing. This relates a bit to the general sustainable dimension, whereby we want to reduce waste and really elongate the lifespan of components within a building. if we are at a stage whereby it doesn't make sense anymore to maintain an existing building and it needs to change, so basically several systems should be studied, right? So replacing an old system with a new one requires, again, a very holistic approach involving not only the mechanical engineer but also the architects and the building specialists, so that multiple dimensions are addressed within this subject. First, there's of course the physical aspect. So where are these elements located? Ducts, pipes, etc. How does that all contribute, or how does it work within the existing setup? And of course, in terms of enhancing comfort, right? So in general, we don't want to look at this element alone. We want to look at it while we study the building envelope, so that we also address the walls and the windows, etc., so that we have a consolidated and strategic, let's say, approach to the building retrofitting. There are many different types and systems to be addressed depending on the typology of the building. So again, this is an interesting opportunity because today we have, the building industry is advancing in a way that it provides more customized and more efficient systems depending on the usage of a space. And of course, lastly, we're very interested in the initial and the operational cost, right? So, and these should also always be seen together, even if the initial cost has a slight increment in terms of cost, because it is, let's say, more efficient or more suited for the project, etc. That should not prohibit the implementation of that system, because if you study the operational cost over the next 25 to 30 years, which should be at least the lifespan of the system, it should show basically that there's a lot of gain and much less energy use over that time frame. Of course, in some contexts, there are incentives that are provided, so actually people go for these systems. PV systems and solar thermal are also interesting elements. Here, there's a notion of scale, so not individual systems are not always the best approach. Sometimes combined systems are much more efficient and prove to be much better, especially if we're studying or looking at more than one building, a group of buildings, or even a neighborhood. So there are always very interesting opportunities to study, so that you get the benefit of the scale and improved performance. Some problems that relate to the pathology, to the actual fabric of the building. First is, in fact, thermal bridging. This is a very common problem, I would say, in Beirut. In many spaces, we see, when there are thermal bridging, we see mold that is created at the edges at the corners in rooms. Of course, this has to be looked at properly in terms of temperature variation, in terms of amounts of relative humidity, and the variation of these two between inside and outside. But again, retrofitting is a very interesting opportunity to solve these problems. Glazed components and frames, the problems associated, again, it's a different form of thermal bridging. And this is kind of easier to notice visually, because we actually see it, particularly when we have metallic profiles and frames. And so this also requires, it's not just, in many cases, the profile is left as a standard profile, but people go for double glazing, and this unfortunately is not enough. The actual frame needs to be thermally broken, and this is again becoming much more common in the market, and the initial cost is not at all prohibitive, right? But it needs to be designed accordingly. The main aim is to have the thermal break, if you like, between the glass and the aluminum continuous, or any kind of profile. And then the third aspect is, in fact, the quality of the glazing, right? The shading factor of the glazing. We refer to this as the solar heat gain coefficient, and this also relates to the amount of radiation that enters. This is also one way of dealing with this, is having low E coating, low emissivity coating, which can prove to be, depending on the orientation of the glazing, can prove to be very interesting. So So it's not necessary. It's often, more often than not, it is not necessary to have low E coating on all the glazing of a project, right? So you can, depending on the orientation, one would assess after a study if low E coating is necessary or not, and it proves to be that it's not necessary on all the orientations. Lighting is a very important component when in retrofitting. Again, there's an opportunity to retrofit in a way whereby we design for visual comfort. We take into account illuminance, the spectral distribution of light and reflectivity. And the idea here is that we actually provide the amount of light that is necessary using the proper types of light sources. Right, so combining these, so first of all, in the passive design approach, we want to make sure that we have enough daylight in the spaces. Even if along the years something was done to disfigure this aspect, it needs to be brought back to its initial kind of condition in terms of daylight. And then we complement that with the electrical lighting. So first, we would like to use lighting less. We want to rely more on natural light. And second, when we use lighting, we want to have the proper fit out, if you like, and then the proper kind of bulb so that it gives exactly what is required. And in this way, we actually reduce the demand for lighting considerably within these buildings. Sorry. The issue of materials, construction materials, is of really primary importance, right? So retrofitting involves the use of a lot of materials, right? So as I mentioned at the beginning, Beirut city has, I think, close to 17,000 buildings. If you calculate that 75% of these buildings were built before the 70s and they are in need of retrofitting, let's say, then that will result in a tremendous amount of use of construction materials, right? In addition to that, explosions such as that of August 4 result in, so tremendous debris, which again results in a lot of construction materials that are out there. The idea is that in this subject and in this topic, we talk about or refer to the term embodied energy, right? And this is the energy that a material will use or that is used throughout the whole life cycle of a material. I'm showing in this diagram the four main stages of a material. So extraction. So where is this component, the building component or material, coming from? Is it from a natural source? Is it recycled material? And then how do we manufacture it to make it into a component that is used in buildings? Does it require low-tech processes and tools, or is it a high-tech process, right? And so does it require a lot of water, for example? Does it require other materials to manufacture this one? Then we go to the installation. So this is, in fact, the lifespan of the building. So once we manufacture it, we take it to the building. How do we actually install this building material? Does it require elaborate machinery? And very importantly also is, what is the amount of maintenance and cleaning and upkeep that is required throughout the next 80 or 90 or 100 years, which is the lifespan of a material? So in the case of existing buildings, of course, I agree that if the building is built in the 1950s, the structure will last for about 70, 80, 90 years. So, there's always a possibility to extend the structure or the building itself, because the structure will allow that. And the proof is that we have many buildings that are of course, older than 80 or 90 years in the city. And then the last phase is the recyclability. So what happens, right? So we will not be around when these buildings arrive to the end of their lifespan. So what will happen to these buildings, right? What are we leaving for the next generations? Is it possible to recycle all the components of that building, whatever we are doing today, right? In the manner of retrofitting. Is it possible to downcycle the materials, right? Can we by using today's retrofitting techniques? Can we have a cradle-to-cradle approach, which is in fact when the lifespan of the building finishes, I undo the materials, if you like. I take down the materials, and then I bring them back as a source for another building, right? And of course, in the middle, there's a star which indicates transport. So transport also contributes a lot to the energy use of a building in calculating the embodied energy of that material. So, we really have to think hard, and there are many opportunities, particularly in our context, to really look at the materials and recycle some of them, reuse some of them. We can reuse them in buildings, we can reuse them in roads. There are many opportunities for this, and we really need to grab these opportunities so that we reduce the embodied energy of this retrofitting process. I have to say a word about rating systems. So there are many rating systems that address existing buildings on the planet. They all relate, there's no secret, they all relate to the type of construction, to the quality and the performance of the walls, the windows, insulation, thermal bridges, the aspects that I have been addressing, the type and efficiency of the heating, ventilation, and air conditioning systems. That actually, as we said, complement the passive design measures, and of course the hot water systems, which really is very easy to decide upon in terms of efficiency and payback period, right? When we do a cost analysis, so of course we can study other rating systems, and we can look at analyze rating systems that exist in other countries. By the way, I will mention that Lebanon has the Lebanon Green Building Council has devised ARS rating system, which is for existing commercial buildings. It is a system which was designed and customized for building types in Lebanon. Okay, it is not a copy of LEED or a copy of BREEAM or any other international system, which are all very well done, but maybe relate more to their context than to ours. In order to establish a solid kind of rating system, if you like, which can also be used as a guide to retrofitting and renovation, if you like, we need to gather a lot more data. So of course, I'm in the process of doing this. I started, a few years ago, but a lot more of this has to be done so that we really enrich a database that describes how walls work in the city. We have numerous types of walls, and these walls have different orientations and different exposures and different window wall ratios, so on and so forth. So documenting with real data these elements is in fact a very important first step, which can go in parallel with the creation of a rating system, and at regular intervals kind of inform and upgrade the requirements or the criteria that have to be respected within the rating system. I will conclude with a few remarks. First of all, the city is a dynamic and living organism. It allows change over time. There is always an opportunity to improve the context, and particularly in Beirut, right? We look at Beirut, of course, today it's not as it should be, let's say, but again, the city will live on for many decades and centuries, and so that by itself is a fantastic opportunity, so that we kind of build on what was done and improve the performance of buildings into the future, of course, existing and in this case, new construction. We always need to have a holistic approach, so the multidisciplinary team needs to look at multiple issues, the thermal, the hygro, so this is referred to as a hygrothermal study, which looks at vapor migration throughout the envelope as well as temperatures, and of course all the mechanical systems and all the other systems that are required to have proper retrofitting. These items should not be studied alone. It should always be a combined effort. Data, again, I cannot stress enough that data is really required. As we saw, it could be very instrumental in informing what needs to be done when we retrofit. And so the different criteria are listed here, but of course there could be others depending on the scope and the capabilities. We need to establish renovation and retrofitting methodologies that relate to particular building types. So what I'm saying is that within one building type, so within one apartment building that is built in the 50s, the actual retrofitting does not have to be the same on all the envelope. Again, depending on exposure, depending on the aspect, the solar aspect, depending on the context, so on and so forth, right? And of course, the use of the spaces. So this kind of articulate analysis can devise methodologies that relate to different building typologies and different use typologies, I should add. Establish applicable guidelines mandated by governmental agencies. So here, it would be great if we have governmental agencies, municipalities, ministries, etc., that can support such an approach, maybe mandated in a certain way, and of course, lastly, create incentives, right, to encourage people to adopt such methodologies. There's a lot of work that needs to be done to educate people on these subjects, to educate inhabitants. This is a long process. It will require changing the behavior of the people so that they understand better how their behavior within a space can improve comfort conditions. Their behavior and their intervention in a space can improve comfort conditions and eventually reduce energy use. So with that, I end. I'm stopping here. Thanks a lot for listening, and I'm ready, of course, to have a discussion about any of the subjects. Yasmin, back to you. Hello?
Yes, I'm sorry.
Okay.
Connection problems. So we have two questions.
Let me escape so that I can see the...
Yes.
Just a second. Okay. Yeah, so... yeah, go ahead.
Okay, so the first question from Sharb Al-Ghanem. Hi, thanks for the interesting presentation. I actually inherited a house that was built in the 1900s, so the thickness of the stone walls and the terracotta tiles of the pitched roof provide a good thermal isolation. But the windows made using Otrani wood are now old and deteriorated and are the main source of energy loss at winter and summertime. Do you recommend to shift to aluminum windows with the same design and color, or try to make repairs, including rebuilding some of the wooden profiles that are in bad shape, noting that repairs would be much more expensive, and I am afraid I will end up with an ameliorated situation without solving the problem? Thank you.
Yeah, sure. Thank you. Thank you very much for this question. So wood is a fantastic material, right? And it's such an important component of the I'll say the word culture, right? Of the cultural dimension of these houses. And it would be, in my view, it would be a pity to replace that with aluminum. Even, in any case, as an architect, I don't really, I don't support the using fake aluminum, right? So fake wood, sorry. So aluminum that looks like wood. Because it's not genuine. So having said that, there are, of course, my answer is to maintain wood as a material. Now, there are very interesting profiles, wood profiles that are actually thermally broken. So that, in fact, do not allow the heat flow from in to out and out to in, depending on the season. So these are, in fact, very interesting. Of course, with the proper glazing, it would be at least double glazing. So that would create a very good thermal barrier between in and out, between the glazing and the thermally broken wooden profile. I understand, of course, the economic aspect that this may be more costly, but again, this is the initial cost, right? So if you were to do a comprehensive study, I mean, I don't know exactly your condition, but other studies have shown that in the coming few years, you will achieve the payback period of the initial system, and from then on, you actually save on energy, right? So this is also saving in terms of energy in different seasons and to an extended time of the year. So without seeing the actual condition, I would say that definitely maintain wood if possible with an improved wood performance, with an improved profile that is made out of wood.
Thank you, Aram. Second question. Hello, thank you for this interesting conference. My question is, why don't we use the term rehabilitation instead of retrofitting?
Yeah, so again, we need to agree on these terms. There are many terms, right? So retrofitting is because it actually it's very confined, right? It is in fact bringing the building as close back as possible to its original situation and adding mechanical and active systems to support the performance, right? So rehabilitation maybe would have different dimensions, right? Because in some cases, as I mentioned, for example, conservation is different, and then preservation is different. So there are a certain number of and they also in fact relate to the degrees of involvement, right? Or degrees of intervention. So if like in many cases in that we saw when the structure is actually fractured, there we have to go for preservation, right? So that the proper term is to preserve the building by fixing the structure, so on and so forth. So I'm saying that there's a hierarchy in terms of intervention, and it's just that the term retrofitting actually pertains to what I'm trying to say, just respecting the initial condition of the building without disfiguring it, yet improving the performance so that people living today are comfortable and people that live in the next decades will be comfortable.
Thank you. I actually have a question. So in the Beiruti house, the ceilings are actually high, and it helped out with the ventilation, and the heat didn't stay in the house. So it used to go back to the ceiling, which was made of Baghdadi, a light partition, and then up to the pitched roof. Right now, in the buildings belonging to the modernist periods and even the contemporary ones, we're actually seeing the floor height being reduced. And does it affect the heat that is staying within the building, within the apartment?
Yeah, Yasmin, excellent. Thank you. Yeah. So in fact, it does. I mean, the high ceilings really contributed significantly to the sensation of comfort, right? So as we know, due to buoyancy, warm air rises. And so the warm air in the space would rise to a certain level whereby the people would remain comfortable while the warm air is in fact at a higher level. We also refer to this as stratification, right? So in some contemporary projects, this is actually done on purpose. You stratify the air so that the warm air does not disturb the thermal comfort of people. In many cases, as you also probably know, there were openings, right? So that the warm air would dissipate towards the outside. Also a very interesting dimension is this, as you mentioned, the wooden Baghdadi roof and the roof tiles. So this in fact create a thermal buffer, right? So this is an airspace on the roof that is a thermal buffer that also reduced the incident solar radiation as opposed to the newer buildings. So these newer buildings, newer quote unquote, as in the 50s, etc., with the lower ceilings, in fact, were subjected to more difficult comfort conditions inside because the stratification did not work anymore. It's interesting to note that so the fact that there were 2 windows per room in some of these projects actually flushed out the heat, and that kind of replaced the issue of stratification. But unfortunately, we do not see that in many buildings, let's say, or at least in all of the buildings. An interesting note is many of the buildings in the 50s, the balcony, in fact, had a parapet. So the parapet, if you, I can't share. Anyway, you know, Zarif, there are so many of these buildings in the Zarif area whereby the parapet of the balcony had a drop, which in fact shaded the balcony, and it was also open, right? It was done in the form of louvers or claustras, or there are so many different ways, so that the warm air in the balcony would actually dissipate outwards. So yes, a very important notion, the issue of stratification of warm air due to buoyancy.
Thank you. So from Sharbel, thank you for the advice. Do you recommend a carpentry contractor or a specialized firm that can help in repairing the wooden windows?
I would need to think about that. I have addressed this issue in a project, in fact. I cannot remember them now, but I can share them with you, Yasmin, if you like, and you can. I really don't remember them now, but yes, there was a company that provided. Of course, this was several years ago. I frankly don't know what's happening today, but yeah, I will dig the name up and I will share it.
Okay, and we'll give it to Sharbel once we have it.
Okay.
Okay, thank you, Aram. That's it for today.
Welcome. Thanks a lot. Thanks, everyone. And I hope to see you soon.
Yes. Thank you so much.
Welcome. Bye-bye.
Bye.